Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So I'm Chaz from Carnegie Mellon, co-PI of the EDDY project with Mark Pepping, the other co-PI. Microsoft, thank you very much for inviting us. This was a work in process for, I guess, maybe 14 years or so. When we started with it with the network model and then just kind of percolating it back up. And over the last 3 years, talking to a number of people here, Terry, Ken, or whatever, about diagnostics. This is, I think, what everyone's kind of dealing with right now is the fact that how do you get a grip on this stuff? And so from different levels in the stacks, and we try to push back a little bit. And this is a story of trying to come at it from a practitioner's point of view, which is agnostic of what domain you're in. It could be security, it could be system, it could be application. And so we'll try to show you what we've done the last couple of years here. So diagnostics, right? You have a flat tire. Discover it, you move on. You have a flat tire a week later. Is it a valve problem? Is it a nail in the driveway? Is some neighbor kid busting my chops? How can you check all the failure possibilities? How expensive is it? Most systems are, made to, out of the box, they run. The hell with diagnostics, right? So why? Things break. Things break to the point where it matters because it's very critical or it's just a pain in the butt every now and then just to keep fixing something. Again, systems are built to just get the damn thing working and keep it going. But, how do you maintain them and fix them after an installation? Only the end diagnostician knows. That is putting in the application, right? There's a lot of pieces in between. There's a lot of pieces that things are really dependent on. But the person who owns that system, they have a lot of the knowledge in their head. And you got to get them the diagnostic data. End user, whoever. Software reuse and layered infrastructures create dynamic dependencies. Yes, diagnostic data may not be available to all. That's one of the problems we've been seeing. Number two, it certainly doesn't follow that service path, right? When I go to some web server, and there's a whole bunch of, there's a database in the back end, there's different networks in the same place, and the data that I'm getting back is not on that same path. And normally, there's a lot of this out-of-band data that you get for diagnostics, but a lot of it, really doesn't answer what you want. And it probably could be extracted if you have a number of these points. So to tackle this problem, we talked to a lot of people like you. The diagnosticians, the engineers, the architects, the end users, and we found these, what we call banes of the system diagnostician. Number one, limited access to the data. The data's out there, but they can't get at it. Number two, how do you discover all this, information when there's just a lot of it? Number three, not only is there a lot of it, but there's different types. Number four, providing evidence for this, what we call non-repudiation. So when we're at CERT or whatever, you get, two entities talking to each other about, well, no, you broke into us. No, you broke into us. And quite, most of the time, no one broke into anyone. It was a third party. Or, with one of our corporate partners, when we work on this type of stuff, they have this great term they call blame storming. I think Terry touched upon this, whereas the networking folks are pointing at the system folks and vice versa, right? And so you need to sing off the same song sheet here to do any type of good diagnostics, an audit record if you may. The last thing here, and I think this is going to hit home with a lot of people here, is, Chaz, we need to find time to develop tools to push it down to lower level people in the organization. But if you could give us an API so that we can throw any data into the system, mesh the data up so we can get it back out to our tools, then you take 50% of our development time off. And the reason why is we keep hearing we have this great tool and it uses this one type of data. So tools are meshed with telemetry. Sometimes a researcher or a tool developer will say, you know what, I wish I could use that type of data too in with my tool and not have to change the tool that much. So hence, who are these people we talk to get all this data? Again, it's the whole kit and caboodle here. It's application support personnel, systems administrators, network support staff, security response folks, managers of computing infrastructures, the help desk, which is very important, and ordinary users. So we kind of had a taxonomy here for thinking about this problem. We've been kind of beating each other up for the last, I don't know how many years on this. And we have kind of four layers of this. Number one, we call it the sensing technology layer. It's, it has state, transaction information. It's basically the ability to collect anything. A light switch goes on, record and log file or whatever. Once you push it up the stack there's this layer that we call orchestration. I think this is the meat of what Eddy's trying to do here. It's, providing data acquisition, normalization, and transport to, getting the data you want, and then in the format that you want it, and then where you want it. Again, you may want it in, two different instances. You may want to split it. You may want to anonymize it because a researcher wants to use the same type of data. So it's this middleware of diagnostics, if you may. Again, up the next level of the stack, diagnostic information. What's the first stage of finding the needle in the haystack of needles? Can you actually do some generic translation and statistical methods to take that data and make information out of it, or just that first layer of knowledge, if you may. Once you have this data, there is this thing that I'll talk about later called the diagnostic life cycle. We've noticed, years ago, just by looking on the wired flow data, we could tell that a daemon died on a specific host, not even having any access to it. Just by looking at network flow data, you can infer so much about what's happening on your network and what users are doing. So you have an immense responsibility with this data to manage it well. So it must be policy driven. A lot of discussion is around that right now, if you have access to all the data. The next level is domain analytics. It's once you have all this data and it's orchestrated in the way you want, now that you can start doing the very interesting stuff of layering it with good AI tools, good visualization tools. But you got to get it to that level first. So what to do? EDDY. EDDY stands for End-to-End Diagnostic Discovery. We pretty much try to do three things. Enable correlation, and we do that with something we call a common event record. And what that is it's a way to format event information to make it easier to process. So we put a header on lots of different type of data. Log file data. We put network flow data, SNMP data, light switch data from embedded systems, or just to be able to collect everything to try to get it easier to correlate. The next thing you want to do after that, we found, is you want to put it into a transport. You want to get it into some backplane that can massage it and then get it to the right place at the right time. And possibly massage it to the point where give it some higher level meetings so you can do very quick analysis. And then provide some simple orchestration methods. Once we normalize it, you can transform it into different types. You can visualize what you have. So think about this as, if you're an electrical engineer and there's this, large backplane, whatever, you want to have to tip probes in certain areas and look at things, right? It's just not end to end. It's actually what may happen in the center points and things like that. We want to store the data, and again, for the researchers, and we can talk about the Dragnet project with Wei, giving them really good data. We found out that just everyone has been clamming up on a lot of this data to do really good research. It's about time that we can give the researchers this information, this diagnostic information, to do the next generation stuff, but in a way that fits policy. A few details. What is a common event record? It's what is seen. There's a type of data that we've seen. We normalize it in such a way it's predictable, so you can pick stuff out of it. It has a unique UID on it. It has the type, severity, timestamps, where it was seen, where it was actually collected from. It's enough to actually get the first level of routing down. So think of the EDDY backplane, and we'll talk about this in a couple more seconds, is Unix pipelining. You got the data coming in, you massage it, you grep it, you awk it or whatever, you do some Perl stuff on it, and you throw it out the other end. You can fork it, split it. You can set it up in the way a diagnostician actually needs. There's this backplane in the middle. We have three components of this backplane. One is an event channel, and it's very high speed. First we decided to do is just tackle this on network flows. And so, we set some high goals here. If we could do it under some high speeds, and it may not be high enough speeds for people in this room, but, we could probably do this and be very effective on the lower end stuff. So an example, we can go around 14,000 events a second. And that may be enough for, mid-sized networks and things like that, but that's where we're kind of going right now. It's a push model, such that, you get what you want, you throw it down the road. very quickly. You don't have to think about it much. And that also helps a lot if you implement this behind firewalls too, because let's say if you're a bank or whatever, you're not allowing people to come in and do the pool type of model, it's actually sending it out the whole way, so you don't have to implement any service or anything like that. We have two other channels. One is the pool channel. And anytime you go into one of our storage agents or whatever, you can query the silo. All right? And there's also a discovery model too where you query, where do I find this type of data? And then the last one is the control channel. And the control channel is just how do you manage these agents? You're going to have this type of orchestration network. You've got to be able to manage it. Yeah.
You said that you normalized.
Yep.
Does that mean that you pull out content from the actual event in whatever proprietary form it is and put it up in the record?
Correct. And we have three different types of the CER in this phase, not our next generation of what we're doing. I'll explain that in a second, but you're right. So in essence, this is the backplane. There's the three channels: control, query, and event, where any agent that we have anonymization agents or normalizing agents, whatever, it uses the event channel. Storage agents basically use the event and the query channel, the event to get the information into it, the query to pull stuff out. Then you can have applications, whatever, just kind of tack onto the backplane. Then we have an agent manager right now. We're developing a backplane manager to manage the whole mesh. In essence, what we try to do is we started out first, slicing and dicing this model under 5 different categories of domains, right? Security, network, application, system, and environment, right? Security events are pretty self-explanatory. IDFs, information protection systems, even flow records, if you may. But we can put flow records in network, SNMP, RMON type of stuff. Applications, web logs, things like that. Systems. Anything in a system log in the way of a disk fault or something like that. Environmental, we had some very interesting interest from the folks in the architecture school at Carnegie Mellon. They have something called the intelligent workplace, where you go in this room and it senses you're in there, light switches go on, things like that. And they had all these different manufacturers giving them all these different sensors. So they said, what, if we can have something normalized to get it to our analysis tools, we could do some very interesting things with it. So we decided, okay, let's test our flexibility. And so we have another CER type here of environmental. So once you get it into the mesh and you normalize it, now this is where the magic begins. And it doesn't have to be, complex management. It can be very simple management. I'll have a demo here for you. But it's just getting the diagnostician the data that they need. There's a lot of it out there. You may not need all of it. So pick it out what you want, get it in a form that you may, and expose it to your tool. These designate the interaction between the event channel and the query channel, such that you may send this to a network management system, an application management system, and a learning system. You may get very interesting data, and it may say, you know what, I want to ask for more deeper type of analysis. So it may go back here to a storage agent and ask some different questions. It may go back here to a normalizer. It may say, you know what, I'm only sampling every 100th packet. Now give me the whole ball of wax for the next 10 minutes. So it's that type of interaction for orchestration. So we tried to address extensibility and scalability here. Scale, because of just the whole load of the different type of data that's out there in the way of different forms. So if we took the philosophy, if you don't need all the data, pick off just what you need. And so again, as I was saying, you have all these different types of events. You normalize it. And to answer your question, the first form of the CER, we put this header on it to provide some level of correlation, and it's the raw payload. We don't do anything except slap the payload on the bottom of it. Then we can go through a transformation area, and now you can specialize this to the point of, if you want to XML the whole thing, you can. If you want to take bits and pieces out of it, you can as well. And then the next layer here is doing kind of a second order transformation, and you can pull a lot of these events together, and you may kick up a larger event like saying, you know what, we're having a denial of service attack right now. And then this type of thing can feed your alerting systems. Forgive me if I'm going a little fast. I have 7 minutes right now. So complications. Scale. Right now on campus, we're seeing, in excess of 10,000 flows a second, so trying to keep up with that. Again, the responsibility of the diagnostic life cycle. Once you have this data, policy must be driven to how you collect it, what you filter out, How do you anonymize it? Do you aggregate it? If you even archive it, and then you have to scour it, because you will be subpoenaed for this data if they know you have it. Data access security. Who gets this data at what point in the thread here? Site configuration. If something changes, you got to change the instrumentation around. You got to change where your probes are at. All right, so that's something that's complicating everything. The next thing is what we're talking about a lot in federated diagnostic analysis. You may want to share this diagnostic data with other entities, both on campus and off campus. How do you do that? How do you set that up? It's very complex. So, here's an illustration right now. You discover your gateway has a routing problem. You furrow an eyebrow a little bit. You fix it and move on. You discover, another routing problem a week later. It's configuration or firmware problem. Downstream BGP problem. Is there a grad student busting my chops? How many potential failure scenarios are there, right? So, what's involved? Peer networks and routers, routing process, on your route server, traffic to and from a route server, through the edge router or not. And maybe, there's resources on the route server that are starved, information from an IBF if you have them. So, what you have here is, here's your network peer. Here, you here in your local network. You have all these things happening. You have log inflow, flow inflow, system inflow. You have these 3 hosts back here. And you know what? It's a botnet. And it's beating up this guy. How do you find that out? And how do you let these folks know that that's beating this up too? That's affecting them down the flow, right? So what we're trying to do here is getting all these different types of events from network security and system in a way that you can, certain entities here can pick out what they want and then possibly translate that into something for a federated management system. So again, what eventually you'll have is combined event flows. So if this is the the EDDY header, you can actually pull out here things that make sense to the right people. Get the data to the diagnostician who needs it. They may see things like systems low on memory. That may be enough. That may be enough to key the right people. Some of the things that we're seeing on this are just throwing configuration data on these events. A lot of the problems you can look at and go back and say, has there been a configuration change within the last hour? And sure enough, that can start the wheels turning in the people's brains. Again, going to a federated event domain. Now you have to do a little bit more anonymization, but it is still extremely useful to tie all these events together into one type of profile. And this is some of the things that we're doing in the next level, such that we look at the behavior on certain systems and how they're acting, or the protocols, and then you build a profile, and then compare that to the next time it's done again. So, in a nutshell, we're trying to wind up here a little bit. What EDDY is. It's an architecture for cross-domain diagnostics. It enables technology that provides, number 1, an event ledger. Number 2, dissemination and correlation infrastructure. And again, a side line of that is, afford research access to this event data. Next, a development platform for diagnostic research. Domain-specific and agnostic. We've developed this to be completely agnostic, not system, not network. That's the real meat of this. And then from there, you can dive into certain tools or certain agents that are very specific to the problem domain. What it is not a management platform. No system, network, application, or security. And it's not the analysis engine, but it enables this analysis. It enables researchers like Wei. So, what are we doing going forward? Ongoing effort. So we're doing, the architecture. The first stage is on it. A solution for integration of the diagnosis, distributed network, and systems. So putting together a framework, building standards right now. We have some corporate partners working with IBM on. They have a system that is fairly similar to ours, but they're interested in the way, how fast we can go and things like that. So working together with them. Trying to produce an open source prototype right now. We have some beta software out right now that you can play with, and it's pretty robust to kind of getting a handle on that to the community. And then on campus, we're starting a center for diagnostic research. So it's being agnostic of doing this type of work and then working with other silos on the university that are people who are diagnosticians in a specific domain, i.e. security, networking, things like that. So campus interactions. Information security office. So I don't know if you can really see this, but just a real simple EDDY app right now. What we do is we take flow data from across the core and outside the network and bring it in, and then we take out of that flow data just what we need. From there, we send that to the Information Security Office. We also take that data, stir off some more things, and, do anonymization in real time, ship it over computer science to Way. And this is the top talkers of what's happening on the network right now. And so this is very valuable. This is anonymized for you, obviously, but the network folks really love this because between the membrane between the Pittsburgh Supercomputer Center on campus, the needle, the needle comes out of the haystack of needles very quickly on what's burning down right now. And so you'll be able to click on this and actually see how many other protocols that you're using right now or services. And then soon what we'll be able to do is click on an IP address here and see all the other connections they're using and possibly other things like that have anything to do with specific first services in the way of log files and things like that. Working, again, with computer science at Dragnet, the School of Architecture, at the SciLab. So what we're trying to do here is expose this to a lot of researchers to see if it can scale, and to see it's very usable. Also with a lot of people at the PDL, which is doing data center analysis, as well as ECE, the CERT, and people at the sensor group doing building analysis. They want to collect sensing data from buildings all around campus and around the Pittsburgh area for fault analysis, things like that. Go ahead.
I think this is a very cool thing that you're doing here, but just what I've seen in some of this analysis that I've been looking in this area, is that a lot of this has to be done from the client side, and you're looking mostly at network data.
No. That was just
a specific,
that's a specific example
here because of the audience. So part of what you see with the people that we're interacting with, there weren't actually any network management people except for we there. The rest of them, the School of Architecture is talking about managing environments in terms of light, heat, HVAC, etc., and they're trying to essentially
what I was thinking about is, for instance, wireless. Often in wireless, you may not actually see that from the server side. You may only see that from the client side, the experience, right? Latency and so on. So do you have instrumented clients as well as instrumented?
So one of the slides that you saw early on was the notion of the layered architecture, right? So you've got sensors at the top or the bottom, depending on how you look at it, and then there's the orchestration of whatever data you get, and then there's sort of generic tools that you can build, and then there's domain-specific analytics. So we basically said it, lay that out, and then say, what EDDY will do, what EDDY is doing essentially is the orchestration. Okay, and so every domain has its set of sensors. Every domain wants to do its analytics, and most people that pick up diagnostics come at it from a specific domain, and they want to get some sensor. They want to get information out, and they want to do analytics on it. And the orchestration of it is an afterthought. It's something that they got to get done. It's the plumbing in order to get there. What we're basically doing, what EDDY is essentially, is an extensible framework to allow you to do that orchestration for whatever domain you have, and then potentially be able to bring those domains together to do domain agnostic analytics. And that's the thing that I think actually is the most exciting about this, is that you can use your algorithms that were written for one domain and experiment with them on other domains, on data from other domains.
So our test bed at the beginning, what we did was, we developed some simple tools, threw on some Windows systems, and actually we're simulating help desk analysis such that when we plugged in a mouse, it showed up in the Diagnosticians workstation or whatever. So we're doing that. In fact, here's something that's exciting for us right now. So we're working at the email message transport. So we're trying to give the email diagnosticians back at Carnegie Mellon a wide variety, such if there is a problem with a specific type of email, they can go in there and get a whole audit record of where the mail went across what machines, to the scours, to the front ends, to the front end POP servers or IMAP servers, all the way back to the murder server, right?
So there's a lot of information in mail logs, but generally the mail logs aren't brought together. Well, you can do that by setting a syslog server and bring the mail logs together, but that still doesn't get you back to other information which is perhaps not in the syslog, that you might want an agent that sits on one of your MTAs to be able to give you queue lengths and various other things that may not be available via the syslog trail itself. So it's about bringing multiple different pieces of data towards the analytic.
And again, we tried the network stuff first because it was the most challenging in the way of scale, but when you're talking about stuff like this, even though the network may be 10,000 a second, this may be 100 a second, which is nothing. Sure.
Have you looked at the problem of tracing a transaction across multiple hops, multiple services?
We have played with that, but what we're focusing on now is actually getting up to the first level of the software, and then we will actually dive
Right,
into
and
it.
again, the main point is that tracing a specific type of transaction across is a domain-specific analytic. And what we're trying to do is provide a better infrastructure to be able to support that kind of thing to happen. So if I want to look at something, I'm going to say, okay, what are my sensors? I need to instrument my sensing capabilities, and then I want to orchestrate it through to bring that data to me, or potentially to distribute my algorithms out to those sensors. So I want to scale it, however that most easily can be done.
Okay. Question back here?
No.
Okay. Want to learn more? There we go.
So the one thing actually to emphasize, I realize that it's not in the slide, is we actually have software on that site. There is a beta release of software, Java stuff, basically, to actually implement this stuff, right? And the stuff that's actually in the software, we must have dropped that slide out of here. We did have a little bit in there about sort of what's included. The main orchestration stuff is there, and there are a couple of analytics and some very simple, or I should say, a couple of normalizers and some simple sort of visualization kind of analytics, like the example that Chaz popped up.
It seems like scalability is the bane of all such data collection systems. So, what do you have to do to address that?
So the specific examples of scaling, we basically try to do two things. One is, one of the things that Chaz displayed there was sort of forward the data that you need, not all data. A lot of systems, when we looked at it, again, when we did our sort of survey of what were people doing, they generally define a domain-based model that includes all these 100 parameters, and then they want to ship that state along sort of periodically. And the point basically is that depending upon your analytic, oftentimes you don't need all that data. You don't need it all. So like Planck, the stuff that they're doing, I don't know, they get like 7 or 8 parameters on actual flow information. And that's it. The model that we have, we use Argus for the probe, actually has like 100 or something, 50 different parameters that are available on a per flow basis, but they, based upon the IRB proposal that they wrote, do not have access to those other parameters. So the idea is we project out only the ones that they want, we anonymize it then, and we forward the stuff along. So you get some scaling that way by, I don't have to forward all the data everywhere. All I have to do is forward along what's of interest in this particular case. So I may have much stronger instrumentation than I choose to use at any given time. So that's first. Secondly, you can actually distribute your processing. You can distribute your analytics around. And so, again, the point of dealing with this as an orchestration system is to say, you know what, I've got those probes out there that are generating a ton of data, and I'm going to actually ship my analytic out to it and allow that to happen locally, and then I'm going to forward stuff along. So the CERT guys, as an example, with their AirCert stuff, that's what they did, and they whined mightily about actually having to do that, but it was the only way that they could actually do it. They had to distribute the analytic and then forward the results, because otherwise it was impossible to scale. So essentially, EDDY is extensible enough to be able to accommodate that kind of model also. So that was the point.
A lot of it also had to do with, with the flow data. How long do you keep this stuff? So when a diagnostician has a problem, let's assume that's a break-in or something like that, it may be, 3 days is enough. And so, taking 3 days of a lot of flow data, which is the most maximum amount, is enough. And then after that, what you have to do with it? So you aggregate it. You put it into bundles that you really think are, are useful to you, or you just save the raw form of the things that are suspicious, right? And so it's so scalability. This is what we tried to tackle first. To us, it was like it's doable. All right?
The other thing that we find is a lot of investigators, when they want to look into these problems, usually what they'll do is they'll try to get to their probe and then dump all that information into a database. They'll grab it for some amount of time, a week, 2 weeks, 3 weeks, and then they quit, and then they go off and try and figure out what the heck's going on. So that's a valuable thing to try and figure out what questions are useful asking. But operationally, you talk to a network manager, mostly they don't care about any event that happened any more than a couple days ago. I mean, and only usually a couple of hours actually is a bigger issue, but it's a couple of days. So in terms of if you have a large flow of events, you spend all your time doing insertions and then deletions of those events. And the point is, I don't actually have any time left to do any queries. So the types of queries, the types of things that I actually want, tend to fall into more of a data flow algorithmic model. So I see I'm going to keep some queue, some circular buffer of 1,000 or 1,000,000 or 1,000,000,000 events, and I'm going to look for patterns in that, but it's a sliding buffer, because otherwise I can't deal with the data.
And that's what Wade's doing right now, to the point where we're giving them real-time stuff. So you may want to do some security analysis on a buffer on a machine that has like maybe 4 gigs or 16 gigs or something like that, and that's enough to keep it for a couple hours or whatever.
And
Then
that's
after
what the
you pitch it.
demonstration was doing.
And that's what we were doing in the demonstration. So you have all these agents, and how fast can we keep up? Can we do with the scale? Questions?
More questions?
Thank you.